And sir, one thing I'm not able to get it, that is maximum independent set. Can you please explain this things once?
Okay, maximum independent set.
Yes, sir.
Okay, okay. And anything?
The negative weighted graph. In weighted graph, how does the negative things work? I'm not able to get it.
So okay, let me give you a small example for that. So orally, okay. So if you are a cab driver, okay. Hello, am I audible?
Yes, sir. I'm listening, sir.
Yes, sir. Audible.
So if you are a cab driver, if you got any savari kind of thing, like uh, if you are traveling to Mumbai from Hyderabad to Mumbai, you are traveling from Hyderabad to Mumbai, and you got one guy like he's paying you some 4,000 rupees, but you are only using 2,000 rupees for petrol. Okay, what happens to the other rest of the 2,000 rupees? Like he's giving you 4,000 and you are spending for 2,000. So what is the other 2,000 represents? Your profit,
Yes, profit.
right?
Huh.
So while you are traveling from Hyderabad to Mumbai, you are actually gaining some amount.
Yes,
Okay,
yes,
but let's say you are only traveling alone and you are paying diesel from Mumbai to Delhi. You are traveling alone. Okay,
hmm. Hmm.
and you have to pay for diesel, right?
Yes,
And there you lose money, like you spend money, you won't gain, you lose.
yes. There's a loss of profit
Uh,
there.
so if you draw a graph where you all are, so you started from Hyderabad and you went Mumbai to Delhi, and Delhi to somewhere like Allahabad to maybe Kolkata, and from Kolkata to Madras, and Madras back to Hyderabad. Okay,
Okay, okay.
so now in few from one place to another place, in few times you got some people, some passengers, but in some places you didn't get any passenger.
Hmm.
Okay,
Hmm.
so in that particular, when you put this particular scenario into your graphical picture where nodes represents the vertices
Hmm.
and the distance, so and from one place to another place when you travel, there is a direct edge from that particular vertex to the other vertex. So what is the weight? Now what will be your weight of each edge?
The money that he spent.
Ah, so you totally want to know how much money you spent, right?
Hmm.
So on each on each edge, you will give a positive weight when you lose money, like when you spend money. Correct.
Okay.
So what is the representation of which one do you represent if you gain money? Like if on one particular traveling, you actually gain money. So if you
Hmm.
are losing money is positive
Then when they're gaining money, that is negative. That's why he's traveling the path once more so that covering the cost.
uh, so you see now profit will be represented as negative of your money. Okay.
Okay.
uh, so in that way, there so weight negative weighted edges are actually opposite of positive weighted, so it actually decreases the weight of the path. So in our
Ah.
case, if you travel along that path, when you get the passengers, you won't lose much, you actually gain somewhat what you lost. So it actually
Hmm.
decreases the burden or decreases the weight. So
Hmm.
negative weights actually decreases the weight. Okay.
Yeah. Now I get it. Now I'm able to get it.
Okay. So did I got the co-host access?
Thank you, sir.
Yeah.
Yes, sir.
Hmm. Okay, let me share. So you asked before weeks. You asked me about
Topological sorting.
topological sorting and as well as uh,
Maximum independence set.
Yes, maximum independence.
Sir, even longest path also, sir.
Longest path is weak level, right? We will cover.
Yes, sir. Yes, sir.
So, yeah, is my screen visible now?
Yes, sir.
Yeah.
Yes, sir, visible.
So, what I thought of is today we will actually do start from longest path and we will cover transitive closure, matrix multiplication, these three topics. If time permits, I thought to go with the shortest paths in weighted graphs and minimum cost spanning. So before that, let me give you what the agenda of today is. So I will start with maybe taking that maximum independent set. And how many of you are having doubt in this particular topic? So one Kajari Saha has raised this issue. Do others also facing the issue regarding this maximum independent set, or so can I have some hand raises if you are facing problem in maximum independent set? Okay, so okay, I guess 3 people.
Sir, and also graded assignment question number 7, sir. I have clarification on the options given.
Okay, so in between we will see the topological sorting also. So how many of you have doubt in topological sorting?
Yes, sir. Me.
Yeah, you asked that, right? Okay, again 3 people. Okay, so we will start with maximum independent set, topological sorting, and we will see graded assignment question 7 in the first maybe half 20 minutes. So till 7:30. And after that, what we will do is we will go and look at what is the longest path in a DAG. So this longest path is actually, what is DAG?
Directed acyclic
Directed
graph.
acyclic
Yeah.
graph.
So longest paths and this topological sortings will only be the applications of a DAG.
DAG.
So we
Yes,
can
sir.
only compute longest path in a graph or any topological sorting of vertices in a graph only for directed acyclic graphs. So no other graphs you can actually sort your vertices in an order, or you can find the longest path in your graph. So this longest path in a DAG we will see, and later we will see the transitive closure. So what exactly this transitive closure means, and we will take an example of this. We will take an example of this also this, and understand what is transitive closure. And finally, let us look at matrix multiplication. So I guess many of you know, but anyway we will recall what matrix multiplication is. And then we have few algorithms to find the shortest paths in weighted graphs. So if there is time, I will discuss what is a weighted graph, and then we will go to the shortest paths in the weighted graph. So there are 3 algorithms mainly. So okay, Dijkstra's algorithm and Bellman-Ford algorithm and Warshall's algorithm. So there are 3 algorithms where all the 3 algorithms will compute shortest paths in the weighted graphs. But there are few restrictions for few algorithms that we will discuss. And then we will see what is, yeah.
For shortest path, we use the BFS, no? Uh,
Okay. See, BFS we will use for normal graphs, non-weighted graphs.
no, yes, no, for non-weighted graph, we can compute shortest path from BFS.
Yeah. See, these are algorithms we will use when the graph is weighted. Weighted
Okay.
graph, each edge has some weight
Yes,
involved.
yes, yes, yes.
So for this, we will use these algorithms to find the shortest paths. And then at last, the last topic of our whole mathematics one is minimum cost spanning tree. We will see spanning tree and
Prince and Kush.
so prims. There are 2 algorithms, prims and Kruskal. So both are very easy algorithms. So you understand
Yes, sir. Yes, sir. That's very easy.
Is enough. Okay. So let's start. So without any delay, let's start. So yeah, I will take up here. So let us start looking at maximum independent set. So what exactly this term tells us? Maximum independent set. So what we have to find? So simply we have to find the largest set of vertices such that the condition follows now, such that no two vertices in my set. So find the largest set. Maybe I will represent largest set. Find the largest set A. So you have to find some largest set A, which is subset of the total number of vertices, such that no two vertices in A should have an direct edge. So it's not directed edge, it's a direct edge. So that means what it says, no two vertices should be adjacent to each other in my largest set, in my set A. So if I pick two vertices, no two vertices, any two vertices I pick, there should not be any common edge connecting between those vertices. So for example, okay. So let's take this is an example of the graph we have. So this particular graph has some 1, 2, 3, 4, 5, 6, 7, 8. So this particular graph is made of 8 vertices and some 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 edges. Okay. So this is a graph of 8 vertices and 11 edges. So let me label the vertices also. 1, 2, 3, 6, 7, and 8. Okay. Now what we have to do, our goal is to find the largest set. So we have to find a set of vertices. And yeah, this set of vertices A should be subset of the vertex set. So out of these 8 vertices, what I have to choose is, I have to choose how many number of vertices I can choose. I have to choose those many number of vertices. I have to put it in a set. And when I choose any 2 vertices in that particular set, I shouldn't have any direct edge connecting between them. So let us pick one choice of it. So let us try to pick one choice. What you do is, you just pick one into your set. Okay, this is like a game. Okay, so treat it like a game. So when you are choosing one in your set, then what all vertices I cannot choose in this particular set?
2, 8,
So when I
2,
am
7,
choosing
8.
2 can't
2,
choose,
7,
8
8.
can't, 7 can't choose.
yeah 2, 7, 8, because when I choose 2, 7, 8, so if I choose
The
2,
adjacent.
yeah, there is an connecting edge between these two. So once I choose one, I cannot choose 2, I cannot
Okay.
choose 8, I cannot choose 7. So
Okay.
then we have left with 3, 4, 5, 6. Okay. So supposedly randomly I choose 3. So all three I can choose, because 1 and 3 there is no common edge. So once I choose 3, I cannot choose few more vertices. So once I choose
Hmm.
3, choose
Okay.
1,
8 and 2, 8, 2, 2, 8 and 4.
4. So 4 also
Okay.
ruled out. So I cannot choose 4 also.
Okay.
Now 5 or 6 I can choose. So let's say we choose 5.
Okay.
Okay. So I choose 5. So once I choose 5,
Then 6
I
is
cannot
also
choose
ruled out.
6 is also ruled out. Okay.
Okay.
So now what all the vertices in my set? So 1, 3, 5 are in
1,
my set.
3, 5.
So yeah, we got 3 vertices in my set. This is an independent set. Okay. So this is an independent set.
Sir, we randomly pick all points.
Yeah, we
That
randomly.
is
No, not randomly. I just started with randomly. So I randomly took one. So if you randomly pick the vertices like this, you will get the independent set. But we need a maximum independent set.
So maximum of all or a single point. Maximum of all or single vertex.
So maximum means, so you have to bring how many number of vertices you bring. See, this is set of 3. So if you got some other set A star which is set of 4, that is maximum than this. Okay, the number of vertices should be large in my set. Okay.
Is it possible that in one set, we first start with 1, that's why this result is something, and if start with 2, the result will be something else?
Yes, correct.
Okay.
So
Then you have to calculate with each and every vertices.
Mm-hmm. See, now let's suppose there is no edges, only 10 edges. Even if I
means,
start from 1.
sir, we pick first randomly. After that, we go to 3. Before that, we choose one vertices. After that, we go through the edge. So here, 1, 2, 3, how to go? Like,
So I just randomly, this is random set.
Okay. Got it.
So we do coloring, right? We do the coloring.
yes,
Yes, sir.
yes.
Yes, sir.
How are we fixing the next vertex, next color, and from where to start? How are you fixing that?
We start one vertex
Yeah,
random.
you start.
After that checking any adjacent node have not the same color. Yeah, like
So
that.
here also we are doing the same thing. Okay. First,
Okay.
but we will get the independent set. Okay. We won't get the maximum directly. It's not the maximum independent set. You will get the independent set. But you need to be sure that that is the maximum. That is the maximum. Matlab, you won't get more than 3 elements in this particular set such that any 2 of the vertices will not have a direct edge. Okay. So for this particular set, if I choose 1, 3 or 3, 5 or 1, 5, there is no direct edge. That I am sure. And if I add one more vertex into this particular set, then this will fail the property of this independent set nature. So I cannot add 2, I cannot add 4, I cannot add 6, 8, 7. I cannot add all of this. So only 1, 3, 5 is a set, and that is an independent set. But that is not maximum. So this is not maximum.
For a maximum, sir, we have to go through all the vertex.
So for that, I will tell you a trick. So if you know how to find the minimum vertex cover, okay.
Yes.
So minimum vertex cover.
Yes, sir. We know.
You know about this, right?
Yes.
So if you find this set, so let's say this is A, then A complement. What is A complement?
The rest of the vertices.
Rest of the
Other than
other than what you have chosen for the minimum vertex cover, other than those, the remaining vertices will form maximum independent set.
So like
interesting, right?
So here 2, 4, 6, 8, 7 will create that.
No, 2, 4, 6, 8 will create the maximum independent set.
Well,
okay, you start with 2. So what happens here? When you start with 2, you cannot give. So now
cannot take 1, 8, 3.
So I have taken 2. I cannot take 1. I cannot take 3. That's it. There are only 2 edges.
Only 2 edges. 1, 3.
1, 3. Now you randomly choose 4, 8 or 7. So I choose 4 now. Okay. Now once I choose 4, I cannot choose
5.
5,
Mm,
right? That's it. So now I am
yes,
left with 7, 8, 6.
yes.
So which one can I choose?
But 6 or 7, anything.
6 or
Six,
7 and 8.
8.
Yes,
Mm,
yes.
So 6, 8 or 2, 4, 7, 8. So these both are
Independence. Max.
maximum independent sets. So you can check there is no edge between 2, 4, 2, 7, 2, 8, 4, 7, 4, 8, 7, 8. So there will not be any
Yes.
edges connecting any of the 2 vertices. And also this is the maximum set I can get. So I cannot get maximum independent set with 5 vertices in this particular graph. Okay. So if you know how to find the minimum vertex cover, then the complement set of the minimum. So let's try to find the minimum vertex cover. So what is the minimum vertex cover we can find? So one I can. So how do you start? So this is also one question. How do you start? Which vertex to be taken for the minimum vertex cover first?
The vertex which has most
Maximum edges, sir.
maximum
edges.
edges.
Yes.
Yes, yes.
So let's say minimum vertex cover set this is. So one has 3 vertices, 3 edges.
Yes.
Also 8 has 3 edges.
Yes.
Also 5 has 3 edges. 3 also has 3 edges. Okay. You
Sir,
choose randomly in your.
one doubt there. Like
Hmm.
initially 6 to 8 there was a edge. So for that, first you took 1, 3, 5. That set is the maximum independent set.
Hmm.
But when you have taken
It's
out
not
the
the
edge,
maximum. It's not the maximum. This is not the maximum. Sorry. This is not maximum independent set. This is only an independent set.
okay.
Okay.
But later you have modified the graph actually. 6 to 8 edge you have taken out.
68. 68 because see that becomes the maximum also. So I just wanted to show the difference between independent set and maximum independent set. So
Okay.
that is why I just removed that edge.
Okay.
So these two are not with respect to the same graph, sir, isn't it?
Which two?
A and A star.
A and A star are this with respect to this only.
No, A previously we got when there is an edge between 6 and 8.
No. Even if there is no edge also, you just see one. You have chosen 1. Then I have
Yes.
chosen 6, 3. I have
Okay.
chosen 5. Can I choose any other vertex?
Oh, it doesn't make any difference.
It doesn't make any difference. So that is
Okay,
why.
sir. Okay, sir. Got it.
So if
Yes,
I
sir.
see the vertex cover of this, so 1 is a vertex cover. Once I choose 1, there is no need of choosing. So this edge is covered, this edge is covered, this edge is covered.
Yes, sir.
Correct? This is how we proceed.
Yes, sir.
So I have to cover this edge, and this edge like this. So now I can choose 3. So next vertex I can choose 3 so that it covers this and this. Correct? 1, 3.
5.
So next I am left with only 1, 2, 3, 4. 4 edges need to be covered. So once I choose 5 into my set, I will cover 3 more. So I have to cover
7.
only 1 edge. So either 7 or
7.
6.
7.
So I can choose 7. So 1, 3, 5, 7 is a minimum vertex cover. So correspondingly, the complement set of this vertex cover set is 2, 4, 6, 8, which will make the maximum independent set.
Okay. Yes.
So if you know how to find minimum vertex cover of any graph, then once you find that minimum vertex cover and just take the complement vertices. So which are not in the minimum
Sir,
vertex.
Sir, excuse me.
Hmm.
In this
Sir.
case, we have got one has 3 edges. Like that, so many are there. I mean, 3 are there. 1, 2, 3, which have got the 3 edges.
Mhm.
So can we start with even 2 also, sir?
So if you start with 2, what it
Because
will make
is there any rule that we have to start with the minimum of that?
you sometimes you see 99% cases you will get the minimum vertex cover, but there will be 1% chances. See, actually, if I talk in deep, if you
Yes.
understand correctly, if you know NP hard, P, so these are like problems we will classify into few bases. So there is a classification thing happens. So P is called P, there is a class P and there is a class NP. So P means polynomial time. Okay. So that means it tells us that what all the problems can be solved in a given time, in a specific time. So I will give you some time if you can able to solve that problem or not. If it is solvable problem, I will put that problem into this particular class. And there is non-polynomial time class which says that even though I give you some how much time you want, there is no specific solution you can actually find and you can actually solve the problem. Okay, every problem will not have a solution. You cannot find the
Time bounded.
yeah, within the time, or even if I give you some time, you cannot actually
Is it
find the
solvable or
solution.
not? Yes.
So this particular vertex cover problem comes under this NP.
Oh.
So see, these are some 8 vertices or 10 vertices which are very small graphs compared to big graphs. So if I have some graph which has 100 vertices and some maybe 2000 edges inside it.
Edges.
Okay, 2000 is possible. 100 into 101 by 2 is the maximum.
Yes, sir.
Then
It is 50 into 101.
50. So
50 into
5050.
Yeah, definitely it will
5050
be
edges.
very much.
So if I have some 100 vertices with 2000 edges inside it, then finding the minimum vertex cover is an unsolvable problem. Okay,
Yes, not
Yes, sir.
you cannot solve it. There is no specific solution for it. Okay,
Yes.
you have to take all the possible combinations of the vertices.
it will take years.
So even the computer cannot solve it directly and give you the solution. Okay, so that is what NP hard class problems are. So that is why in the small graphs, what we actually can do is we can actually start with one vertex, and correspondingly you can find one set which may not be the minimum, and you take other, so just the other vertex, next vertex, and you find the vertex cover. So within some 3-4 possible cases, you will actually get the minimum vertex cover.
Oh, it means that we have to check for all the 3, 1, 2, 3.
You have to check.
Okay. Okay. That's my doubt, sir. Actually, why we have to go for only one? Why not?
No. You can go for 2, 3.
Yes,
but
out of the 3, we have to see.
You have to see which one you will get the minimum vertex.
Yes, sir. I got it.
Sir,
Thank you.
one doubt. Like we could have, like it is possible that we can have in like maximum independent limit, we can have less element compared to independent set. So it is possible. Like
that is what we sound, right? This is maximum independent set, and there is also an independent set which is 135. 135 is an independent set.
Yes, I got it, but it is possible that independent set is bigger than maximum independent set.
No. See, that if it is bigger, then that will be the maximum independent set, not this. Okay. So now,
sir, I have one more doubt, sir. Sir, you told here minimum vertex cover is 1357 for this graph.
Yes, sir.
But here, sir, we have maximum independent set is 2468. You told just contradiction of minimum vertex cover is the maximum independent set. So if we take minimum vertex cover is 1357, then we will have only 2, 4, and 6 as the maximum independent set.
Why?
You told, sir, earlier, so that's
sir,
why
you wrote
I
it. So, sir, if A is the minimum vertex cover, then A complement will be the maximum independent set.
Yeah. So 1357 are the vertices in minimum vertex cover. What is the complement vertices? Which are the complement vertices?
2, 4, 6 only, no, sir. Which are not in
8
that
is
set.
still there, na? 8.
8 is also not there, right? 8 is also not
8
there.
Also.
Cover, right?
Okay.
So it will be 2, 4, 6, 8. Like
see, out of 8 vertices, if 4 vertices are in my vertex minimum vertex cover, there should be another 4 vertices which are not in this vertex cover.
Okay, sir.
So it will be equal, like minimum and maximum.
Minimum?
Like elements in the minimum will be 4 and elements.
No, this is vertex cover. This is minimum vertex cover, and this is maximum independent set.
Okay.
Both are different.
Yes, but
okay. So Yeah, so this minimum is like optimizing this vertex cover. Maximum is optimization for independent set. So we want maximum independent set, not the minimum independent set. Minimum independent set has no use. Okay. We try to find maximum. So we try to optimize the independent set by maximum, by getting maximum. And we try to optimize vertex cover by getting minimum. So how many minimum vertices are needed so that I can cover all the edges, and how many vertices are there in my graph such that they are independent to each other. So how many maximum vertices. So that is the difference between vertex cover and independence.
Okay,
And
got
connection
it.
is this. So once you find minimum vertex cover, complement of it will be the maximum independence.
Okay.
Okay. Yeah, that is
Sir, for the minimum vertex cover, we just need to select one vertex from each edge. That is the principle there.
so yeah, that is what we do. So that is what vertex cover also says. Every edge need to be covered.
Yes, a minimum vertex cover and minimum independent set is different thing. Yes.
Maximum independent. Yeah. So
Okay,
understood?
okay. Yeah,
Understood about maximum independent set?
Yes, sir, totally. Thank you, sir.
Okay, let's go to topological sorting. So what it says, so it actually says, if I have given you a graph, so if I give you the graph, so graph G is given, and also this is DAG. So for this we need to check first. So check whether it is directed acyclic graph or not. Okay. Once you are confirmed that it is DAG, then you can perform this topological sorting. If not DAG, so okay, I have the slides anyway. So let us see what is a directed acyclic graph first. So what is a directed acyclic graph? DAG. What it says, without any directed cycles is called a DAG, correct? So it should be directed, and also there should not be any directed cycles inside.
Yes, sir.
Correct? That is the DAG. So no cycles inside the graph, and also the graph should be a directed graph. So that is what directed acyclic. So I will give you a minute or two. Just identify which one is DAG. So there are two graphs given to you. Which one is DAG and which one is not a DAG. So let's say left side is the graph, first graph, or let me name it. So it's a graph.
Second one is not a DAG.
B graph. Okay.
B1 is not a DAG because B forms
Yes, sir,
cycle
B1,
from B
sir.
to C, C to D, D to B.
Okay.
Yes.
Okay.
G1, sir.
Get 0 to 4, 4 to Q, 3 to
G1 is
1 form a
not a
cycle,
DAG.
sir.
B, C, and D.
Okay. B, C, and D forms a cycle in G2. So, okay, G2 is not a DAG. Everyone convinced with that?
Yes,
Yes,
sir.
yes,
See
sir.
here. So B to C, C to D.
Even G1 is also, sir, because 0 to 4, 4 to 3, 3 to 1.
Sir, both are not DAG.
0 to 4.
Both are not there.
Okay, 0 to 4.
No, there is no cycle. There is no
Now-
cycle.
Now tell me whether G. So this is not graph. Everyone convinced. Not DAG.
So G1 is a DAG.
Whether G1 is DAG or not a DAG.
G1 is also not DAG.
DAG or not DAG.
No, not DAG.
So
4 to 3.
4 to 3.
3 to 0, 0 to 4.
3 to 0, is there a directed?
No, sorry.
Okay, just check whether
It
this
is
is
DAG.
Sir, it's 0, 1, 3 form a cycle, no, sir, here.
0,
In
1,
this
3.
graph. Yeah.
So 0 to 3, okay.
3 to
So
1.
can I go from 3 to 1? Yes, okay.
No,
Can I
it's
I
go
think
from
that
1
this is
to 0?
DAG. There is no cycle. I'm not
there
able
is
to
no
find.
cycle.
Yeah. So if you are
G1 is a DAG, sir.
yes, correct. So D,
G1 is
it is a DAG.
Yes, sir. G1 is DAG.
So if you are that confused whether it is a DAG or identifying cycle, if it is difficult, then use this topological sorting algorithm. So you try to sort so what this topological sorting says us is,
Remove the vertex which is
minimum the vertex
yes,
was
which
minimum
in degree, like
out
which we
minimum
don't.
minimum in degree or 0 in degree.
Okay.
Yes, 0 in
So,
degree.
Okay, okay, you are telling the process. So what
yeah.
are we actually doing? So what are we actually doing? What is this topological sorting does actually? Final output, what is the output?
It is a set of that, like create
So
the
it
set.
is a sequence of vertices. Okay. So what we do, we actually keep all the vertices in a sequence such that there will not be any back edges. Do you remember back edge? What did back edge mean? So if I have
Yes,
some sequence like A, B, C, D, if I have this sequence, I have sorted like this.
So this is the dependency thing. So that
Dependency. Okay. Okay. You call it dependency, or if you don't want to call it dependency, whatever the edges in my graph are there, that should be only from left side vertex to the right side vertex. There should not be any edge that is connected from the right side vertex to the left side vertex in my
yes,
sequence.
not possible. Yeah,
So
because
in my sequence, that is how I should arrange my sequence, and that sequence
yeah,
is nothing but topological sorting.
yes. So that A, B and C is dependent on A. If A is not able, not finished, then B and C not able to execute.
So that so in the lectures, sir has introduced one
yes,
term called
sir.
Yes,
dependency.
sir. Yes,
Yes, sir.
sir. Yes.
So dependency means, so you see this direct edge, right? So that dependency means this particular vertex 1 is dependent on this particular vertex 0.
0,
So if
0.
there is a direct edge from vertex I to vertex j, what it represents is, if there is a direct edge from vertex I to vertex j, then what it tells is, what this particular direct edge tells is, then j is dependent
Dependent
on I. So whether it is task or whether it is anything other task or maybe courses. So in the
yes.
example like courses,
Yes, sir. Courses.
Something which has to be done in a particular manner. Like,
prerequisite. So
yes.
prerequisite kind of thing. When it is course, it is like prerequisite. When it is task, it is dependent. So there are few more examples like task, okay, dependent, prerequisite, okay.
Like
What
making a
else?
recipe, it is
Building
also.
a
Making a
house.
recipe. Yes, correct. Making a
Building a
recipe.
house.
Building a house or making a
So,
recipe. Making a recipe, you start without pouring oil into your pan. You cannot directly cook, right? So there is some dependencies. So first you should do one thing, and next you should do the other thing. Like this dependency. So there will be a direct edge. If there is a direct edge from vertex I to vertex j in your graph, then we say j is dependent on I. And this particular sequence, we are writing it like, so whichever is not dependent, we will write that particular vertex, and whatever the vertex comes to the next of the, so there is B, right? So this particular E is either dependent on A, B, C, D. So A, B, C, D should be completed first, and then only I can perform E. That is what this sequence says. So if you don't understand this, just understand what I said. So you have to keep the vertices, you have to order these vertices in the sequence such that there should not be any edge in your graph, so that it comes from the right side vertex to the previous already you have arranged the vertex. So that is what we are going to do. So in order to do this, we have to do few things first. So that is what called initialization. So what is the initialization, or before starting the thing, we fix some things. So setup, maybe we call like setup. So we need to do some setups. So for that, first and foremost thing is you compute. So first and foremost thing is, so these are initialization or the setup what we are doing. So what we are going to do is, you compute all the indegrees of vertices in the graph. So this is the first and foremost step we are going to do. So what are the in degrees? Just tell me one by one. So what is the in degree of 0?
1.
One.
In
One,
degree
sir.
is 1.
In
One.
degree is 1. So only one edge is coming towards 0.
Yes.
So the
Yes.
in degree is 1. So what is the in degree of vertex 1?
2.
2.
2.
Okay, 2. 2
Zero.
0.
for 3
2.
2.
2.
and for 4
2.
2.
2. Correct. So our first initialization step is compute all the in degrees. The second step is, so from here the algorithm starts, the sorting. So whatever the thing we are going to do, it will start. So we pick the vertex
0 in degree.
which has
0
0 in degree. So what if there is no 0 in degree?
2.
Vertex 2.
No. What if, my question is, what if in your graph, if there is no 0 in degree?
That is
No
not DAG.
incoming edges.
There is no incoming edges.
There are no.
Then it is not DAG, sir. It is
This
not
is
DAG.
not NAG,
That's not a
DAG.
DAG, sir.
So the one fact of DAG is basically
One vertex should
there
have in
will be
degree 0.
there will be at least one vertex which has in degree
In
0.
degree 0.
Okay, yeah. So this is a DAG because there is a vertex 2 which has in degree 0. So we have to pick that vertex 2 now. So we have to pick that vertex.
And sir, there also must be a vertex which has out degree 0. So
Out degree 0 also is one thing.
yes.
Okay.
Hello, sir.
Hmm.
I joined little late, sir. Can you please little explain what is difference between topological sorting and topological sequence? So
Both are same.
same thing. Okay.
Same thing. Topological sorting or topological sequence, both are same.
Okay.
So topological sorting or sequence. Okay. So what you do is, once you have the vertex with you, you add that vertex to your topological sequence. So 2
Right.
comes into your topological sequence. And the next step is, what we do is, we just
We need to remove 2 and all the connection connected to it 2.
So what we do is,
Then the in degree are going to reduce.
Decrease.
so what you do is, you remove the vertex. So let's say pick the vertex I, so which has in degree 0. So remove the vertex I and all the edges that are incident with vertex I. Okay, what are we going to do? We are not only removing the vertex, we are removing the vertex
Yes.
as well as
And the edges also.
Decreasing the
Edges
in
who are
degree.
connected to 2.
So these 2 edges we will remove. Okay, as
Yes.
well as this vertex 2, we will remove these these two edges also. So if I remove, this is how it will be. So once
Yes,
you
sir.
remove, and there is one more step you have to do. After you remove, what you do is,
In
you
degree of
update,
0 will be 0 and in degree of 4 will be 1.
you update the
degree in degree.
in degrees of
Vertex which were connected from that vertex.
connected to the removed vertex, or you just simply say update the in degrees of all the remaining vertices.
Yes.
Okay, what you do is you update, and the final step is, the fifth step is the repetition. So repeat from 2 to 4. Step 2 to step 4. That means you again pick a vertex which has in degree 0 and you remove that vertex and all the edges that are incident to vertex and you update the in degrees. So between I just forgot one thing. So once you pick the vertex I which has in degree 0, add it to the topological sequence. Okay, TS means topological sequence. So this is what we repeat this. We repeat the cycle step 2 to step 4. So now you see here. So once I am updating the in degrees of these 4 remaining vertices, which vertices ka in degrees will actually update?
0 and 4.
0 and 4. Or you simply compute. So in degree of 0 will be 0 now. And in degree of 4 will be 1.
1.
And remaining 1 and 3 will be as it is only. There will not be any updation.
Yes.
So what you have to do? You have to choose. So now we have to repeat the step from 2.
For
Second
0.
Step. So you pick the vertex I which has 0 in degree. So 0 in degree vertex is 0. So then you add it to the topological sequence. So I added it to the topological sequence. So once I add, what I have to do? Just go to the step 3. So remove the vertex I and all the edges that are incident to vertex I. Now I is 0. So 0 as well as all the incident edges I will remove. And next is update the in degrees of all the remaining vertices.
Yes, then 4 will be 0, 3 will be 1, and 1 will be
This
1.
is 1 and this will also be 1. So now again we have to repeat the process. Pick the vertex I which has 0 in degree. So which one has the 0 in degree? Vertex 4 has the 0 in degree.
4.
And I have to
And
add
it
that
to
the topological
TS.
sequence. And next is I have to remove 4 as well as the edges that are incident to that. So and the fourth step is update the in degrees. So when I update, this will be 0 and this is 1 as it is. So next what I have to do, I have to repeat again. So pick vertex I which has 0 in degree. So now 3 has in degree 0. So I will add 3.
Sir, if we get this question in test having 6 or 7 vertices, then we have to repeat graph again and again after removing? It will take a lot of time.
So if you don't want to repeat, you just cross out the edges in the graph itself. Hello?
Yes, sir. We can simply just cross the edges which were.
Yeah. You just simply cross out, man. No need to actually remove and draw the new graph. Just simply cross it out. Something like that. So it's just for your clarity and not to go wrong in the question. You just simply draw the graph. It won't take much time. You don't need to be accurate, right? It don't need to be like a straight line and exactly a circle. Right? If you understand it, you can simply draw it as quick as possible. Okay? Right. It doesn't cost much time. Okay, so this is what the topological sorting or sequence for that particular graph. So but that is what, if you are confused with whether this is a DAG or not, just try to find the topological sequence. Just try to arrange the vertices in the order, dependency order. If you are able to arrange, or if you are able to get at least one topological sequence, then that is a DAG.
Okay. Sir, for a DAG, there will, for at any step, right? We only have one vertices with 0, or
No, not necessary. You in some stages you might get 2 vertices which is in degree 0.
So we can go random in that case.
You can go random, but in questions, some places we will give whether you should take alphabetical order or numerical order.
Okay, so we'll follow that. Okay,
yeah,
sir.
you have to follow that. If not given, you can randomly take either of it, and that will be a possible topological sequence.
Okay.
Out of 2 or 3 possible topological sequences, one you have found it. So in the questions, maybe this is a possible topological sequence. Then you have to check whether that can be a possible topological sequence or not.
Okay. Yes.
Yeah. So this is about topological sorting. Okay. So if you are confused with whether that is a DAG, if the graph is big, like 10 vertices, and you are unable to find the cycle inside it. So simple method is you just find the you just try to find the topological sequence. If you are able to find the topological sequence, then that is a DAG. If you are unable to find the topological sequence, where you are unable to find, when you are stuck with choosing the vertex I. So at some position in your process, at some position, there will not be any vertex which will have in degree 0. If it is not a DAG, there is a cycle. And if it is a cycle, everything will have an incoming edge. So if everything has an incoming edge, every vertex will have at least greater than 0 in degree, and you won't get a vertex which has 0 in degree. So in that particular cases, you will stop doing this topological sorting or sequence, finding this, and you simply say this is not a DAG. You will find the cycle inside it. Okay, clear?
Yes, sir.
Okay.
Yes, sir.
Sir, the conclusion is like if we can find the topological sorting, then it is a
DAG.
DAG. Okay. And it will not form an inner circle, like no direction it can have a cycle.
Yes, correct.
The parallel, can we go for longest path, sir?
Yes. So in this particular lecture, in this particular week, we started with longest path, right?
No. Why, when we were doing this topological sorting,
parallel you can do longest
that's what
path.
I'm parallel.
Yeah.
Go for the longest path
Yeah,
also, sir,
parallel
because in graded assignment, one question it is given like that, step
Yes.
after the step.
Correct. So you can parallelly find topological sorting as well as the longest path. Okay. So yeah, see these facts you all know, I guess. DAGs does not have cycles. Okay. And every DAG has a vertex with in degree 0. This is pakka. You know, in order to be a DAG, first and foremost thing is the in degree must be 0. Okay. And also
Yes,
you
sir.
can say, you can simply check here in this particular graph. Okay, there are no out degree. So every DAG has a vertex which has out degree 0. So if you compute the out degrees of this particular, all the 5 vertices, so no, there will not be any vertex which has out degree 0. You can compute out degree of this is 1, 2, this is 1, this is 1, and this is 1. See, you see, so there is no vertex which has out degree 0. So this is not a DAG. So you can simply, by finding in degrees and out degrees only, you can actually guess somewhat. Okay, somewhat whether the given graph is DAG or not. So every DAG has in degree vertex, in degree 0 vertex, out degree 0 vertex, and also topological sorting and longest paths can be solved on DAGs, only on DAGs. So this is also one fact about that DAG. So if you can able to find this topological sorting and longest path too, then that says that the given graph is a DAG. If you are unable to solve, then those are not DAGs.
So I think one more condition should be added, that all the nodes should be connected, because if one node also is
Okay.
independent.
Let me tell you one thing. So whatever the graphs, these DAGs, or in future like shortest paths, when we are computing the shortest paths, whatever this week 10 next half part and week 11 complete path, we deal with only connected graphs. Okay. Connected. So you know what is connected graphs, right?
Yes, sir.
So we usually deal with connected graphs only. So that is why we never mention that as a separate thing. Okay, whatever you said is I agree. Okay, but in this particular course, we actually deal with only the connected graphs. So that means it evidently says that every vertex is connected. Okay, somewhat connected, or there will be an edge. Okay. For your satisfaction, I will add that thing also. So graph should be connected. That is what you said, right? Connected, right?
Yes, sir.
Okay. So yeah. So what is your name? Yeah, as Neha said, yeah. Even the graph should be connected. Okay, let's see what is the longest path in this particular. Okay, Omkumar, any doubt?
Sir,
No, sir.
Sir, in the previous topic, like if we are not able to find the topological sorting, and we were trying to correlate this with various real life problem like the post enrollment or cooking, things like that. Does it mean that we cannot solve that those problem, or what is the
See, whatever the applications we discussed, that falls under dependency trees only. See, this course example is also a dependency tree. There will not be any three courses such that one is dependent on the other. So if it is like that, how will you start?
Okay.
Correct. So whatever the applications we have discussed, those all fall under this dependency trees only, like this DAGs case only. Those will fall in these cases only. Okay.
Okay.
Those ever does not follow this particular thing, we will not discuss. Those are not the applications of these DAGs. Okay. Whatever we discuss, those are the applications of DAG, real life applications of DAG. Okay. Yeah, let us see how to find this longest path in a DAG. And before finding that thing, what is the longest path? So what actually, when you see the term longest path, what comes into your mind? Like longest path, what does mean?
Farthest.
Maximum number of edges.
To reach from one vertex to another.
In layman's term, it is the
We have to
farthest.
go for maximum number of edges.
Okay, maximum number of edges.
Yeah, maximum distance between two edges.
Shubhashri, one. Hello?
Hello.
Shubhashri, you are saying something. Shubhashri. Hello? Am I audible?
Yes, sir, you are audible.
Yes, sir. Yes, sir.
Then Shubhashri is not audible to me.
Okay.
Okay. So yeah, whatever you said is correct. So we are trying to find the longest path with respect to edges. So the longest path in the graph. So that means if I see any graph, I am going to find the longest possible path. And I guarantee that there will not be any path which is longer than this path. This is the longest in the path in the
So
graph.
why one should want to compute longest path? I mean, there should be there should be must application of this.
See, that is what, right? So there is a courses, there is an example professor has taken courses. If you wanted to do some degree, study some degree, maybe 3 years degree, and each in that degree you have to go through some courses, and some courses depend on another courses. There are prerequisites for each of the courses, and you just wanted to know how much time will it take in order to complete all the courses. So that how much time takes is what the longest path applications.
Okay.
And also in the graded assignment, you might have seen the task performing question. So there is a girl who performs some tasks, and some tasks can be performed at a time. But how much time will it take in order to complete all the tasks? So these all are applications of longest path.
Okay.
Okay. Yeah. So yeah, let's compute the longest path in the in a DAG. So these longest paths, what we are referring, only can be computed in the DAG. Okay, I'm stressing this because many people will get confused. Even if we give a directed cyclic graph, many people will start computing the longest path. Many people will start the topological sorting, and they actually compute, and they will actually give us the sequence. And yeah, so there are cases like this. So that is why I'm stressing this longest path 2 and the topological sorting only computed in DAGs. So let us see how to compute this. So these are our, so whatever the step 1, step 2 are there, these are again the initialization things. So these are the steps or initialization things. So what we do is, before we start performing or before we start computing the longest path in a DAG, we actually compute in degree for every vertex I in the DAG. So this is the same thing which we did for topological sorting. Is called an initialization. We give. So we are going to give some number each and every graph. So that particular number represents the longest path to. So we are initializing. This is the longest path to somewhere all the cost. So this is the initialization we do. So what we are going to do? So now we have two numbers associated to each vertex, correct? So one number represents the in degree and another number represents the longest path to. So there will be two numbers associated to every vertex in the graph. So this 0.1 and 0.2. 0.1 gives us one number to every vertex. 0.2 gives us one more number to every vertex. So there are two numbers associated to every vertex. Now this is the setup we made. So we have given two numbers. One is in degree and one is longest path to. Then what are we going to do? Then what we are going to do is you find a vertex u with in degree 0. This is what we did in topological sorting also. The same thing here also. We find a vertex which has in degree 0 and remove it from the diagram. So we are going to remove it from the diagram. And the next thing what we do is
update the in degree.
We add this vertex u to the topological sorting. Okay, sorting and give the longest path to u value. So whatever the longest path to u is there, so we will give that number to that particular vertex u. And then what we do is we update the in degrees of all the vertices that are adjacent to the vertex u. So which are all the adjacent to vertex u, you will update the in degrees. Till here, it is similar to the topological sorting. Till step 4, it is same as it is what we did for topological sorting. The only change happens in the step 5. So not only we update the in degrees, we also update the other number which we have given, the longest path to I. So these I are adjacent to you. So all the i's, all the vertices which are adjacent to you, we are going to update this longest path to I as. So this is the formula you can remember, or whatever the professor's formula, if you know, if you understand, the professor gave one formula, right? So if you understand that, it's okay, go with that. If you don't understand that, this is what we are going to do. So we are going to compute the maximum of between two numbers. So one number is previously whatever the longest path to I is there, value is there, that is what we are going to take. And the other one is 1 plus the longest path to u. So whatever the vertex you are removing, so there will be a longest path to that vertex u, right? So we will add 1 to it and we will take the maximum out of it. So either this longest path to I or 1 plus longest path to u, whichever is maximum, we will take that. And that particular number we will update to the longest path to I, where I is the adjacent vertices of u. All the adjacent vertices of u, we will update it. So this is
So
what we are
what
going.
adjacent vertex means it is the neighbor vertex or incoming?
Neighbor. Adjacent means there is an edge connecting between these two vertices. Okay. Yeah. So for all vertex I that are adjacent to vertex u, we are going to update this. And next, what we are going to do is we are going to repeat step 3, step 4, step 5 until all the vertices are removed from the given diagram. Okay.
So can you please give one example?
What you did in the step 3, later you added some additional, add u to topological sorting.
Add u to the topological sorting and associate or give the number which is the longest path to u. So we will compute, there are two numbers, right? One is in degree and other is longest path to I. So that is the initialization we did. So there will be two numbers associated to every vertex. So we will remove that vertex u, and as well as we will give the longest path to value to that particular vertex. And then we will update the integrity. So I will take an example and I will explain so that will be clear. So now this is a small example we have. Okay. So first step is every vertex in the DAG. So let's compute. So whatever the graph we have taken, that is the same graph. So this is 0. I will quickly write. This is 0. This is 2. This is 1, 2, 2. Correct? These are the integers.
Yes, sir.
Yes, sir.
Correct. So the second step is we are going to initialize longest path to every vertex is equals to 0. So now adding to this blue numbers, we have another numbers, and the initially all the red numbers are 0. So red numbers indicates the longest path to that vertex. So till now we initialize that longest path to vertex 0 or vertex 1 or vertex 4 or vertex 3. The longest path is 0. So that is what the number significance is.
Can you repeat, sir, please, the last one, the longest path?
So we are going to initialize for every vertex, we are giving 0 as the longest path. So we didn't start the process. Before starting the process, this is the initialization we do. What we say is the longest path to every vertex is 0.
Okay.
Okay, that is what our initialization is.
Okay.
And then from here, our process starts. So the third step is find a vertex u with in degree 0. So which has in degree 0 vertex?
2.
So blue.
2.
2. So once you find the vertex 2, so this is the topological sorting, and this is the longest path to that vertex I. So once you find 2, what we are going to do is we are going to add the 2 to the topological sorting, and the longest path to 2 we will give it as we will associate to that 2. So the longest path to 2 is, as of now, what is the longest path to 2?
0.
0, sir.
So that particular 0 we are going to give to this particular vertex 2. Okay. Once you do that, we are done with step 3. Then we will go to step 4. Step 4 says we have to update the integers for all the vertices that are adjacent to vertex U. So once you remove it, once if you remove 2 as well as the incident edges, after removing that, what we are going to do, we are going to update the integers of all the adjacent vertices of that 2. So there 0 and 4 are the adjacent vertices. So we are going to update the integers of this. So this will be
0.
0. So after
0
updating,
and
this
1.
will be
and this
1.
will be 1. So we are done with step 4 also. Now come to the step 5. So now we are going to update the longest path to I, to vertex I. So I is the adjacent vertices to U, which is the removed vertex. So we are going to update it as max of the longest path to I, comma 1 plus longest path to U. So now in this case, I is 0 and 4. So 0 and 4 are the two vertices which are adjacent to U. U is 2. So the vertex which we removed is 2, and the adjacent vertices are 0 and 4. So I have to update the longest path to 0 as max of longest path to 0 or 1 plus longest path to 2. So you see here,
Sir, in the previous step, how did you derive that longest path is 0? Longest path
That is
0
the
only.
initial value we have given, right? That is the initialization. We have given 0 to every vertex.
Okay, so we have selected 2 and longest path 0.
To 2 at that particular, yeah, at that particular moment when I am removing 2, the longest path to 2 is 0. So that is the value I will give it to 2. That's it.
Okay.
Sir, in the second step, the longest path of 0, right? The 0 is a vertex or a degree, sir?
Vertex.
Okay.
So this 0 is vertex. This I represents the vertex here. I and U are the vertices. Okay. So the longest path to 0 is equals to the max of longest path to 0 comma 1 plus longest path to 2. So what is the longest path to 0 as of now we have?
0.
Longest path to 0 we have 0.
0, sir.
1 plus longest path to 2. What is the longest path to 2?
0.
0. So what is max of
1?
0 comma 1? 1. So the longest path to 0 we will update to 1 from 0. So the red number from 0 to 1, it will go to 1. It will update to 1. So this
Sir,
will
can
be,
you please explain the last step? Actually, I could not get properly.
so it's actually the maximum of the longest path to 0 till now what we have, or 1 plus the longest path to the vertex we remove.
Yeah.
So either of the maximum we will take. The longest path to 2 actually we removed the vertex 2. Okay,
Yes,
vertex
yes.
2 is removed.
Yes.
So once you are removing the vertex 2, now U is 2.
Okay.
Okay, and what are the adjacent vertices of 2? 0 and 4. So you can see 0 and 4 are the adjacent vertices. So we are going to update the longest path to 0 and as well as longest path to 4.
Yes.
Okay, those numbers we are going to update. As we updated the indegrees, these blue numbers, likewise we are going to update the red numbers also. Okay.
Sir, but why we are taking
Why we are taking
max of longest path to I?
because we are trying to get the longest. So we are trying to maximize.
Okay.
Trying to get the maximum farthest or okay. If you take the minimum, it doesn't make sense.
Yes, it will not make sense. So basically, longest path actually means number of edges connecting to that vertex, means how many edges you have to cross to visit that vertex.
Yes.
Can I think that?
So from one vertex to another vertex, how much longest path you can pick? How many edges
How many
you can
maximum edges
maximum
we
edges
can
you
take?
can pick? Okay.
Okay.
Yeah.
Sir, in the second graph, what is 1 next to 0? Out degree is 0. What is 1 there?
Which one?
In the second graph after taking out 2. Yeah. What is 1 there?
1 is the longest path to 0. See, this red number represents. So blue is
Okay, after the derivation. Okay.
in degree. And the red one is the longest path to that vertex I. Okay, in degree of I. In degree of I. This is blue number indicates the in degree of I and red number indicates the longest path to I. So what it says is, in order to reach to 0, longest path I can have is only of length 1. This is what it says. So in order to reach 0, you can check. So in order to reach 0, only from vertex 2 you can reach to 0. So there is no other edge which actually comes towards 0. So from 2 only I can come to 0. And the longest path to 0 I can have is from 2 to 0. That's it. This is the longest path. There is no other path that comes to 0 which is more than 1, length of more than 1. Correct?
Yes, sir.
You can see from the graph only. So the longest path to this particular vertex 0 I can have is of length 1 only, not more than that. And also this particular 2 to 0, this 0 is there, right, for vertex 2. What it says is the longest path to reach vertex 2 is actually 0. I cannot reach vertex 2 at all. There is no path that reaches to vertex 2. Is that true or false?
Yes, sir.
Yes, sir.
Right?
Yes.
So
Yes.
there is no edge that comes towards 2. So there will not be any longest path to vertex 2. That means there will not be any path to reach 2. The longest path is 0. Similarly, the longest path to 0 vertex, the vertex 0 is 1 of length 1 only. There is no other path which has more than one length, and also it reaches to 0. That is what it tells us. Okay, and next is the longest path. What we do is the longest path to 4. It is actually max of, so what it will be, max of longest
Longest path
path
of
to
4,
comma
4.
1 plus
Longest path of 0.
longest path to
2.
2.
Yeah. So whatever the vertex we removed, 2 is the vertex we removed. Okay, we are updating 0 and 4.
Okay. So one quick question in this step now. Though we have two adjacency vertices 0 and 4 from 2, the reason why we picked 0 is because the integrity was 0. Is that the reason?
No. You have to
calculate
update
it for
both.
both.
You have to update both. Even if you update 4 first and 0 next also,
Okay.
doesn't matter.
Okay.
Anyway, we are doing updation for both the vertices. I just
Okay.
randomly choose 0. You can choose 4 and later you can update 0. Okay.
Okay.
So now what is max of longest path to 4 is, what is the red number?
This step, what we have done now, it will always give 1, right? Like this in the second stage of the sorting, when we are doing the LPT of 0,
yes, correct.
this will always give 1.
Give 1, yeah. That is correct. So this is 0 and this is 1 plus, this is longest path to 2 is 0.
0.
The max of 1 is 1. Okay. So you will understand better in with vertex 4, I hope, because you see the longest path to 4 now got updated from 0 to 4. Okay. So what it tells us is, so now until now the longest path I found is, in order to reach 4, is from 2 to 4. From vertex 2 to 4 and the edge 2, 4 is the longest path. That is what we found out till now. That is why the longest path to 4 is 1. So that means you can reach to 4 with one edge. There is a path of length 1, and that is the longest path to reach 4 as of now. Okay. That remember. So now initially we thought 0 is there is no path to reach 4. That is why we have given longest path to 4 as 0. Then when we removed vertex 2 and when we used this formula and when we computed the longest path to 4, it actually gave us 1. It got updated to 1. So we found, while we are removing vertex 2, we found two paths, and that is why from that two paths, corresponding to those two paths, there are, see, these numbers got updated, and it says that in order to reach 4, the longest path is edge 2, 4. So that is why it is 1. And also to reach 0, the longest path is edge 0, 2, 0, 2 edge. So that is the longest path we have. So till now, that is why this is 1, this is 1, and other things are 0 as it is. Nothing will update. Okay. After that, what we are going to do, once we update this longest path to every vertex I that are adjacent to you, we are going to repeat step 3, 4, 5. So what is step 3? Now find a vertex u with in degree 0. Correct. So now in this graph, what is the vertex with in degree 0?
0.
0. Correct. 0 is the vertex. So what we are going to do, we are going to remove 0 as well as the incident edges to 0, and we are going to add 0 to the topological sequence, and the number which has for longest path to 0, we will add it to the longest path. Okay. Now it happens. So the topological sorting and the longest path to I, it will be like this: 2, 0, and this is 0, and the number associated to 0, the longest path to 0 is till now, while we are removing 0, the longest path to 0 we have is 1 only.
1.
So that 1 will come here. This is 2, 0, and 0, 1. So now what we are doing, we are actually removing 0
Vertices.
as well as those edges, and we are going to update in degree of incident adjacent vertices. So this will become 0 and this will become 1. Now the next step is we are going to
Why,
update the
sir?
long
Why it will become okay? We are not updating the longest path. We are updating the.
we just updated only the in degrees. Now we are going to update. So now the
For vertices 1 also it will be 1, no sir?
yeah, correct. So even this will be 1. So now we have to update the longest path to the adjacent vertices, which are 1, 4, 1, 3, 4. So all the 3 vertices are adjacent to. Now u is the removed vertex is 0.
0.
And the adjacent vertices are 1, 3, 4. So now we have to update the longest path to 1 and the longest path to 3 and the longest path to 4. Correct? All the adjacent vertices need to be updated. So what is the longest path to 1? This will be max of longest path to 1 comma 1 plus longest path to 2. Which one will come here?
2, sir.
2.
Sir,
Two
sir,
or zero?
one doubt there. 2, 0, only 4 and 1 was adjacent. Why? Oh, 2, 3 was also okay. 3 was connected, right?
3 is also adjacent.
Yeah,
You
yeah.
can see that.
Yes.
So will it be 0 or 2?
0.
0, sir.
0.
Zero.
Recently removed.
Yeah, recently removed. Whatever the vertex we removed, that will be the u. So this will be 0. So now tell me, what is the max of longest path to 1? Till now, what
0.
is the longest path to
0.
1? It is 0. And 1 plus
1.
longest path to 0. So
1.
what is the longest path to 0? We have 1. So you see this. So once you are updating topological sorting and longest path numbers, so longest path to 0 is 1. So 1 plus 1. So max of 1 plus max of this will be max of 0 comma 2. So what will be the value?
2.
2, sir.
So you see directly for vertex 1 from 0 to it got updated to 2. So you update it to 2. Okay. And what is the longest path to 3? Now let's compute the longest path to 3. So this will be
Sir,
max
this longest path that we have calculated for 1 is from 0 or 2?
from 2, right? From 2. So now you see, so this particular 2 represents, so whatever the 2 you got, so till reaching 0, the longest path is 1. Okay, that is what it tells you. And from 0 to 2, 0 to 1, and there is one more edge. So in order to reach 1, from 2, 2 to 0, 0 to 1 is the longest path till now we found for vertex 1. Till now. So that is why the number is only 2 till now. Okay. So till now, so as of now, we got the longest path to 1 as 2, which represents that 2 to 0 is one edge. And once you reach 0, 0 to 1 is one more edge. So therefore, I got longest path to 1 as 2. So that is the longest path as of now I found. So I didn't finish yet. We are going to finish. Once you finish, the last number which you have is the longest path.
Okay.
Okay. Now it is 2. So let's compute quickly. Longest path to 3, comma 1 plus longest path to 4, 0. So max of longest path to the 0, 1 plus 1. So even this is also 2.
2.
And what will this be? Max of longest path to 4, comma 1 plus longest path to 0.
3.
Will be max of, what is the longest path to 4 we have till now?
1.
1. 1. See this red number. 1, comma 1 plus, what is the longest path to 0 we have? 1.
1.
So it is max of 1 comma 2. So what it
2.
will be?
2.
2. This is, now this will update to 2. Now this will update to 2. So have you observed vertex 4 till now? So initially the longest path to vertex 4 is 0. We initialized it. Later, after removing one edge, it got updated to 1. Longest path to vertex 4 updated to 1. And then when you remove one more vertex, the longest path to vertex 4 got updated to 2. What it tells us is, while you are removing 2, it actually computes the longest paths from 2 to every other vertex. So initially we have 2 to 4 is the only known longest path. So that is why the number associated to 4 is 1. Now once we have also included 0, now we know all the edges incident to 0, all the edges incident to 2. So with respect to all these edges, the longest path will be from 2 to 0, 0 to 4. So there are two paths from 0, which is from 2 to 4 directly, and also from 2 to 0 and 0 to 4. So among these two, which one is the largest path, longest path?
2 to 0 to 0 to 4, sir.
2 to
2
4.
to 0 to 0 to 4.
Yeah.
So that is what we are going to do. So that is why we take the maximum. If you choose the minimum, it will give you the shortest path.
Yes, sir.
Okay, so that is why we choose the maximum out of it. Out of the two paths, which one is the largest path, longest path? So that is why that is what this 2 number represents. So there is a longest path of length 2 in order to reach vertex 4. And that path is, the longest path to 4 is from 2 to 0 and from 0 to 4. So this is the longest path to 4. For vertex 4, this is the longest path. There is no other path that actually reaches to 4 and also greater than length 2. Okay, understood? Now can you help me to compute the rest of the things?
Yes, sir.
Okay.
Next, we will go for 4. Longest
Next we
path
will go for 4.
from
Because
4.
the integrity of vertex 4 is 0 now. We will add topological sort 4 to the topological sorting. And what is the number we are going to give for 4?
2, sir. 2.
2. So that when you are removing the vertex, what is the number the longest path is associated, that number you will give it to the longest path.
Okay.
So you will remove and update the longest paths of, oh sorry. So once you remove this, we are going to update the integers. So the adjacent vertex is only 3 now.
Yeah.
So I will be only 3 and u is 4.
4.
4.
So the longest path to 3 will be max of
Longest path
to
to
3,
3
comma 1 plus longest path to 4.
4.
So this is max of longest path to 3 we have till now is 2.
2.
2, comma
1
1
plus
plus
2.
longest path to 4 we have is 2. See this.
2, so 3.
So it is max of 2 comma 3.
2, 3.
3.
3.
So this will get updated to 3. Okay.
Now next we will take 3.
Now we will remove. So now we have topological sorting and longest path to vertexes. So this particular thing will be like 2, 0, 4. Now 3 also adds into this. And this is 0, 1, 2, and 3 is 3.
3.
Okay, now we are going to remove 3 and update the longest path. So once you remove 3, we will have something like 1, and this is 0, and the blue number is 2 now. So what are we going to do now? I is, so the vertex need to be updated is 1, and the vertex
One.
which we removed now till now is recently is 3. So the longest path to 1 will be max of
longest path.
Longest
path
to
to
1
1
plus longest path
1 plus longest
1,
path to
3.
3. So max of longest path to 1 is 2 till now, and 1 plus longest path to 3 is 3.
3.
This will be max of 2 comma 4.
4.
So it will be 4. So we will add 1 to the topological sequence. 0, 1, 2, 3, 4. So you see, in order to reach 1, the longest path to 1 is 4. That means, so for reaching 1, there is a path of length 4, and which implies, so that is the longest path. In order to reach 2, the longest path is 0. In order to reach 0, the longest path is 1. In order to reach 4, the
Not
longest path is 2.
graph.
For 3, for the longest path I can have to reach vertex 3 is 3. For vertex 1, I have the longest path and of length 4. So you see the graph, the longest path will be from 2 to 0, 0 to 4, 4 to 3, 3 to 1. So 2 to 0, 0 to 4, 4 to 3, 3 to 1. So this is the longest path in the graph.
Sir, can't we have other longest path also?
No, you cannot have.
Sir,
That is what we find out. In this
yeah,
particular graph, this is the longest graph.
sir,
Longest. Yeah.
rather than going through all this process, if we just derive the topological sort and then we count the edges, then that will also give the same result, right?
Not particularly. Sometimes what happens is same in the topological sequence, these two may have the same value, same longest paths. So 4 and 3 can have the same longest path, 2 and 2. Did you understand? So it will not be always 0, 1, 2, 3, 4. So one number will be given to one vertex. It will not be like that. So sometimes the longest path to more than 2 vertices can be same.
Okay.
Okay. So, but say, yeah, some logic you can apply. You find the, if you are convinced that this is a DAG, and also you find the in degree vertex and the out degree 0 vertex, out degree 0 vertex and in degree 0 vertex. So between those two only the longest path will have. The longest path will be. So this is the in degree 0 vertex, and this is the out degree 0 vertex. So the longest path will be from in degree 0 vertex to the out degree 0 vertex in a DAG. You can
Is
directly
it like
evaluate
always?
Or will it be for all graphs, sir?
for all
For all
graphs.
DAGs.
For all DAGs, yeah.
So
For all
we
DAGs.
can use it as a shortcut.
Shortcut, yeah, maybe.
Okay.
See, you can actually prove this. Proving is very simple. For suppose this is not the out degree 0 vertex. Okay. Something else. So from something else, you can actually reach to the out degree vertex 0. Then that will be the longest path. You think logically. If the longest path is not ended at out degree 0 vertex, then from that vertex to out degree vertex 0, there will be a path. So for suppose this longest path got ended at 3. If this is a vertex which has out degree non-zero out degree, then from here, there is a path to out degree 0 vertex. And if you include that, that will become the longest. And then contradiction comes.
Yes.
So definitely the longest path will be from in degree vertex 0 to the out degree vertex 0. Okay, this is how we compute the longest path, and I have one big example for you. So now you have to tell me the topological sequence as well as the longest path in this graph. Okay, what is the first and foremost thing we do?
In degrees.
In degree 0.
Sign in degree.
I will write the in degrees. Correct me if I am going wrong. Correct or wrong?
Yeah, correct.
Correct.
Correct. Okay. Now the next step is we are going to give one more number to every other vertex.
Longest path.
Longest path, and we initialize the value to be
0.
Okay. Now what we have to do?
We have to put 0 into topological sorting. Sorry, B.
Longest path.
So B I will put in the topological sorting. And what is the number, the longest path to B I will give?
0, sir.
0. Okay. The next step, what is the next step?
So we'll remove B, sir.
Okay,
And
we remove B.
And
update that difference. What's
keep this graph as it is. Let's do it below. Okay, let's compute here so that the graph will be as it is. So we are going to remove B. And next, what we are going to do?
Update in degrees.
Updating in degree.
Will be 0. This will be 0. And this will be 0. Next, what we are going to do? What is the removed vertex U?
U is B, sir.
Are B and E are they not connected, sir?
B and E are connected, right? So that is why
we have removed B, no, sir.
We have removed B.
So E also should be removed.
No. Why E removed?
Only B will remove.
Only B. So there is only one vertex which has
yes, sir. Yes.
So we remove B and update the in degrees.
Update the in degrees. Okay.
Yeah. So now you see. So the adjacent vertices are C, D, and E. Correct?
Yes, sir.
So the longest path to be updated to the vertices C, D, E. Correct?
Yes, sir.
Yes.
By using the formula max of. So if I wanted to find the longest path to C, so it will be max of longest path to C, comma 1 plus longest path to
B.
Whatever the vertex we removed.
Yes.
So this is max of C. Longest path to C is 0. And 1 plus longest path to B is whatever the vertex we removed. It is
0.
This will be 1. Similarly, for D also it will be the same.
Yes, sir.
For E also it will be the same.
Yes, sir.
Okay, you can check it. So everything will get updated to 1.
Alright.
So 1, 1, 1. Yeah. Now what we do? So there are now two vertices which has in degree 0. What can we do? So in these cases, you randomly choose. If nothing is mentioned in the question, you randomly choose either C, either D, whichever you like, which letter you like, you choose it. If it is given, let us say, let's fix. If it is given that in alphabetical order. Okay. So if in the question is given alphabetical order, so what we are going to do? We are going to take C.
Remove C.
Remove C and add C, and longest path to C is 1. So after updating this topological sequence and longest path to, we will remove C.
Then I will become A, E, and H.
Right. Now we are going to, now I will become I will become A, E, H. So you see the adjacent vertices of C. That's it. A,
Yeah.
E, H. So those are the I
Will be C,
and
sir.
U will be C. Correct?
Yes, sir.
So now
Yes.
we update the in degrees of the adjacent vertices. Okay. So this is 3. This will update to 3. This will update to 0. This will also update to 0. Now we have to update the longest path to A, E and H.
Yeah.
Correct. So the longest path to A. This will be max of longest path to A, comma 1 plus longest path to
C.
C. So this will be max of
0,
0, comma 1 plus longest path to C is 1.
1. So 2, sir.
So this will be 2. So similarly, it will be, so for E, it will be like max of 1, comma 1 plus 1.
Yeah.
So the longest path to 1 plus the longest path to C is 1.
Yeah.
So it will be max of 1, comma 2. It will be 2. So this will get updated to 2. This will be 2. So A we just found out it is 2. For this also it will be
2.
2. So max of 0, comma 2. We will get 0, comma 2 and it will be 2. So now which vertex we are going to take?
Yes, sir.
Yeah. So there are now 3 vertices which has in degree 0.
Yeah.
And as we mentioned, we are going by alphabetical order. So there are A, D and E. Alphabetically A comes first. So we are going to remove A and we are going to give the number, the longest path to A. While we are removing it is 2. So we'll give it 2. And we are going to remove A as well as the adjacent incident edges. Now our I will be J and F.
Yes, sir.
Yes, sir.
And U will be A. And we are going to update the integers. Now this is 0.
This is 1.
This is 1. And the longest path will be max of, this is max of 0, comma 1 plus A is 2.
2.
So it will be 3.
3, sir.
And here also it will be max of
0,
0, comma 1 plus 2.
2.
This is also 3. Now finally we are going to get here we are going to get 3 and 3. Okay. So next what is the next step?
D.
So D, E, J. Among D, E, J, D comes first. So D.
Yes.
And the longest path to D is
1.
1.
1. Okay. So D is 1. And the next step is we are going to remove D and update the in degrees as well as the longest one. So we will remove this. So by now everyone understood what we are doing. So this is the repeated process we are going to do.
Yes.
And the same process.
Yes, sir.
So we remove and we update the in degrees of the adjacent vertices. And we are going to update the longest path. So here you see this is max of 0, comma 1 plus 1. So now U is D, I is H and
I.
capital I. So you see the adjacent vertices of D is H and I.
H and I, right?
Okay, so I is H and I and U is D. So when we remove D, the longest path to D is 1. So this will be max of 0, comma 1 plus 1, which will be 2. Correct? So this will be 2. Now you see H. H has 2 already. So this will be max of 2, comma 1 plus, what is the longest path to D? It is 1.
1.
So what is max of 2, comma 2?
2.
2, sir.
2 only. So you see previously also it is 2, but after updation also it doesn't change, it remained as 2 only. Okay, so what it tells us is there are two paths which are of length 2 only, like from B to D, D to H, and from B to C, C to H, both are of length 2. So till now, that is why max of 2 comma 2 is 2 only, either of it is the longest path till now. So B to C, C to H, so these are the vertices we removed, B, C, D. So corresponding to that, B to C, C to H is one longest path to H, and B to D, D to H is another longest path to H. So that is why we got max of 2 comma 2. So either of it is the maximum. And now what is the next step we are going to do? We are simply going to take E. So now we have E, J, I as 0 degree in degree vertices. So E. So E longest path is 2. So after that we are going to update. So update now I is only H and U is E. Correct? So the in degree of H we are going to update it to 1. And the longest path is max of 2 comma 1 plus the longest path to E. It is 2. So max of 2 comma 3 is 3. Now the maximum got updated. So it updated to 3. And this 3 corresponds to this particular path. B to C, C to E, E to H. So this is the longest path to H now. As of now, it is of length 3. So that is why the longest path to H is updating continuously. So now I and J, which one we are going to remove? I.
I.
Right. So I comes here, and the longest path to I is 2. And once we remove I, so G is here, and the vertex which we removed is I. So G in degree we are going to update it to 1, and it is max of
0 plus 1
0
plus.
comma 1 plus longest path to I is 2. So this is 3. So max of 0 comma 3 is 3.
3.
So this will be 3. So the next step is we remove J. We are going to remove J. Okay. And J has longest path to as 3. And now I becomes H again. So you see how many times H is getting updated. So now this is J. And now once I update it, this will be 0. And now I have to update max of 3 comma 1 plus longest path to J. What is longest path to J? 3. So max of 3 comma 4.
4.
What it will be? Now 4.
Sir, any shortcut for this longest path?
This is the shortcut. What is the shortcut?
And it's a repetitive task again
It's a
and
repeated
again.
task. That is what we do. That's it. So you see now we got the longest path to H as 4. And the path is B to C, C to A to J, J to H.
Yes.
So now this is the longest path to H I can have. Okay, so that is why H longest path is 4.
We can move to G, longest path.
So from here you can actually write it like this, from J to J, H, F. Next we are going to remove F, and last we will remove G. Correct? So as the longest path to H is 4, from 4 you see max of 3 comma 1 plus 4, it will be 5. Max of 3 comma 5 will be 5. So this will be 5 and this will be 6.
Sir, if we were going alphabetically, then we should have gone to E after E, F.
After E?
EHIJ.
See, alphabetical order only matters when you are struck with 2 or more in degree 0 things.
Okay.
Okay. Yeah. So now have everyone understood how I wrote this? So once you perform
Yes, sir.
this thing, it will get like that. So you have to remove this and you update it to 0. So and also you update this. This will be max of 3 comma 5. So 3 comma 1 plus 4 max, and this will be 0, and this will come to 5, and this is 0, and then 5 will come here. F we will add to the topological sequence 5, and this will be 3 comma 1 plus 5, max of 3 comma 1 plus 5, and that will be 6.
That is 6.
Okay, so we until all vertices are removed. So we removed everything. So we are done. So this is the topological sequence, and the longest path, maximum longest path we had to G, which is of length 6. Okay, if you want to find the longest path, you start with G. Okay, you start with G and you trace back, you go back. So this is the longest path from G. You go back, just go back to the, if it is 6, you just go back to the 5, and then you go back to 4, and then you go back to 3. One, two, three, 4, 5, 6. So this is the longest path in this given DAG. So which is of length 6. You cannot have any other path which is more than of length 6.
Sir.
And also you observe the longest path is from in degree 0 vertex to the out degree 0 vertex.
Yes, sir.
Okay.
Sir, then longest path should be from B to G, right? Not G to B.
Because B to G only the longest path.
Yeah. G to B to G, sir.
B to G only. So in order to find the longest path, you just trace back. You just go back from G to B, and the path is from
B to G.
B. Path is from B to C to A to J to H to F and to G. So this is the longest path. This is the longest path you can have in the graph.
Yes.
Okay.
That topological sequence, right? The topological sequence. What do we get here? This is the longest, right?
No. In between there will not be some vertices. D, H, D, I will not be in the longest path. Even E will not be in the longest path.
Okay.
Sir, I didn't get how to trace back.
See, you just go from 6 to 5, 5 to 4, 4 to 3, 3 to 2. So once you reach 3, J, from J you just go back with the edge that follows. It will go back to A. From A you just go back to C. You just go back to B. So that is.
So the longest path may be different from the topological order, right?
Maybe different from the topological order.
Sir, when going tracing
some vertices will.
Some vertices will lie and some vertices will not lie.
Will not be there.
Okay.
Sir, while tracing back here, I and E have same two to no, sir. Then we have to choose any one.
I and E and A has 2. Okay.
Yes, sir.
Now from J, where you can go, you have to see. From J, can you go to I? Can you trace back to I?
No, sir.
No. Can you trace back to E?
No.
You can only trace back to A.
Yes.
Okay,
yes.
sir.
Correct. Once you go back to A, now 2 is also covered from 3 to 2. Once you go back to 2, there is 1.
అలేదని నేను 10:30కి వస్తానని చెప్పా మేడంకి. అయితే వాణి మేడం కూడా చెప్దాం అంటే ఫోన్ స్విచ్ ఆఫ్ వస్తుంది.
Okay. So that is how you trace back.
Okay, thanks.
Okay. I will just explain what transitive closure is, and we will end the session today. And we will look the other parts in the next session. We have slides for the algorithm, so don't need to worry about algorithm.
Okay, one intersection there. Like in the final exam, how many problems will be asked? 15 or more?
15.
15, huh? Okay.
So maybe subparts, if you include, it will be like 18. 18 or 17. Okay. And we will give you the weightage. Has weightage has been given? No, right?
No,
As
sir.
of now, no.
Sir.
No, sir.
You gave some hint in the last class. You told
That
that
not that in official announcement has
no,
happened.
No, sir. No, sir. Wiki sir told us that more question will come from 10, 11 weeks because
Yeah.
they are not even tested right now. So
And
more
9 also,
will
be
be from there.
Week
Yes, sir.
9
9,
also.
9,
Told
10,
or
11, right?
I told
9,
or
10, 11.
you are speaking with
Vicky sir told last.
Even I told.
Okay, you told. Okay.
So, he's not able to. Okay.
Yeah.
Okay.
Okay.
So we will give you official will happen. So I will just discuss what transitive closure is, and we will do the rest of the things in the next class. Okay. Or shall we do the transitive closure in the next class itself?
Sir, I haven't started transitive closure, so
Okay,
maybe.
then
We'll do it next class, sir.
Next class, sir.
Then
Next
we will
class,
do
sir.
transitive closure in the next class. Okay.
Sir,
Yes,
in
sir.
examination, we have to find the longest path using the method you have told. If we will take and remove each time and draw new graph each time, it will take a lot of time. So, is there any different way to do that?
See, that is what. See, if you practice multiple problems, you will get a direct idea where to start and where to how we can get the longest path. So by looking
Okay,
at
sir.
the graph only, you can easily find the in degree vertex 0. So this is a method
Hmm.
we follow. Once you get that, you can simply see this B has the in degree vertex 0. Okay, B. So the
Hmm.
longest path starts from B. From here
And
there
out
are
degree
three paths
0.
to go. From here there are three paths to go. So if you choose this path, you will go to D, go to H, F, and G. You can come like this here. So the
Yes, sir.
longest path is 4 only, right? From B
Hmm.
to D, D to H, H to F, and F to G. Okay, if I
Hmm.
go this is how it is. Or if I go from B to D, D to I, so also you see the out degree. So I have to start from B and I have to reach G. That is what you have to do.
Okay.
Okay. In order to go there, I have many paths. B to D, D to I to G is one path. B to D, D to H, H to F, F to G is one path. B, C, C, H, F, F, G. B, E,
So,
H,
so
H,
that
F, F.
visually,
Out of
and
all,
we can
out of
start.
all these possible things, you have to
Hmm.
choose the longest one.
Okay.
Okay. So from here,
Hmm.
there are three paths. So if I go here, I am getting only 3 and 4. What if I
Hmm.
go to C? From C, I can go to A or H. Correct? There are
Yes.
two. So if I come to H again, that is like it is giving me only 3 or 4. So I
Yes.
can go to H, A. So once I go to A, I can come directly to F, or I can in between I can reach two more vertices. Which one is the longest I will get?
Two
Like
more.
this. Like this, you have to you from the looking at the graph only you can 95% longest path you will directly looking at the graph you can find out. So from B to C,
Okay.
C to A to J. Okay, this is giving me the longest, and bagi other things will give you lesser than this path only. Okay.
Yes.
So yeah, that comes that intuition and that thing comes only when you practice a lot. So you
Okay, sir.
randomly take graph. So no need to be like someone should give you the graph. So that is the
Hmm.
advantage of this graph theory. You randomly take one, whatever you feel, you just fix some vertices. Whatever
Hmm.
you just randomly give edges. Make sure that is a DAG and try to find the longest path. So whatever
Okay.
that is your graph. You made the graph now. So it will be interesting to find whatever you made. Okay.
Okay. So any graph I can make and I can start it with that. Once.
Start finding the longest path. Start finding the topological sorting. Take the undirected graphs and try to play with try to get the maximum independent set. And look at
Okay.
if I remove one edge or if I add one more edge, whether the
Hmm.
maximum independent set or is keeping changing or it is same like this.
Hmm.
Okay.
Okay. Sir,
Okay.
graded assignment means maths graded assignment date is 24. Will it be extended or will it be 24?
24 is fine, right?
Sir.
Is it not fine?
No, sir.
No, sir. 24
No, sir.
how? It
We
is
are left
20.
with only 2 days to cover four subjects.
No. Last date is on 27th, na?
No, 24.
No,
it
sir.
is
Sunday.
24th, coming Sunday, sir.
Okay,
This will not be considered, no? This will not be considered, no? That this.
For grading we will consider, but not for NTEM eligibility, I guess.
Okay.
We will push this graded assignment deadline. We already gave this to 27th. See, because also we have the sessions on Monday and Tuesday, na?
Sir, graded assignment, how it is coming to the final grading? Actually, there is
We are taking some best 6 out of all the 11. Best 6 or 7 out of all the 11 assignments. And we are going to take the 10% of that score.
So 10% will come to that. Okay.
Excuse me, sir. Sir, what is the weightage of interim exam of all this? Like in static around that week 9 to 9 onwards, it will be covered 70%.
Not that much, but we will cover somewhere around 40 to 50 maybe. We will give you the official announcement. Okay?
Sir, so one quick question. So term and weightage will be 50%, graded assignment 10%, and quiz 1 and quiz 2 is carrying 40%. Is this understanding correct?
Yeah.
Okay.
Okay.
Then the graded assignment date will be 27th for this week.
Yeah, 27th. I will ask them to update. We actually gave the date as 27th.
Okay, sir, because it's the first session for week 11.
Yeah. Correct. So even we will extend.
Because we have so many lectures to cover also, sir. Only half were done.
Right. We will extend it. Don't worry.
Thank you, sir. Thank you.
Okay.
So the next session will be on Monday, sir.
Monday, right? Monday. Okay. Chalo then.
Thank you,
Thanks
sir.
for joining.
Thank you, sir.
Thank you.
Bye.
Have a great day ahead, sir.
Same to you.
Thank you, sir.
Thanks a lot.
Hello. Hello.